So hi everyone. So previously we had discussed on the extended Euclidean algorithm, right? So today, as I've said earlier, so we will be making or we will be discussing the this one modular exponentiation algorithm. Yeah, just give me a second here. Yeah. So today we'll be going with the modular exponentiation algorithm. Yeah. Let's get into the definition part one. Let's see what the definition part states here. Yeah. Right. So modular exponentiation efficiently computes a to the power of b. Yeah. A to the power of b mod m. A to the power of b mod m without ever forming the huge number a to the power of b. Without ever forming the huge number a to the power of b. Yeah. So it uses binary exponentiation, nothing but exponentiation by squaring. Right. So when I say binary exponentiation, it is nothing but the exponentiation by squaring just to reduce the number of multiplications to the big of log b. Just to reduce the number of multiplications to the big of logarithmic b. Yeah, this is very important. Reduce the number of multiplications to big of logarithmic b. So this is very important. Just remember. Yeah. So let's get into the explanation part here. So let's see what's the key idea here. So let's write the exponent in the binary and repeatedly square the base while consuming bits of the exponent, right? So this is fine, I believe. What we'll be doing, we'll be writing the exponent in binary and repeatedly squaring the base actually while consuming bits of the exponent. Yep. So keep a running result initialized to 1. So always keep a running result actually, resulting variable that's initialized to 1. This is fine. Yep. Easy peasy. Next, let's we have to reduce the base. Reduce the base that is equivalent to the base modulo mod, right? So this is very important. Just remember this. We have to reduce the base that is equivalent to the base modulo mod at the start just to avoid the large numbers. Just to avoid the large numbers. Yes, this is fine. Now for each bit of the exponent, from the least significant to the most significant. Yeah. So for each bit of the exponent from least significant to the most, this one, if the bit is 1, suppose if the bit is 1, multiply the result, nothing but result into base modulo mod. For each bit of exponent from least significant to most, if the bit is 1, then what we need to do, we have to multiply the result, nothing but result into base modulo mod. Yeah. So square base equals base into base, nothing but modulo mod. These two steps you have to keep in mind. Just remember this one. The exact same thing will be implementing in the form of code. Yeah. Shift exponent. Then we have to shift the exponent right by 1 bit. Then we have to shift the exponent right by 1 bit. Yeah. So this is the this one. What do we call? This is the idea basically. The same exact same thing will be implementing or articulating in the form of code. Yeah, you don't have to worry, right? So this uses big of log b multiplications and always keeps the intermediate values below mod into mod. Yep, so this is fine, I believe. So it's fast and memory efficient as well, right? So many languages, right? So we are making use of the Python here. So we can just go with the Python power of this one POW of a comma b mod implement the same idea natively, right? So we can directly go with POW power, nothing but the power of a comma b mod. So these basically Python, this implements the same idea natively, right? So now we have the idea. Let's do one thing. Let's start writing the code or the let's start writing the algorithm. Yep. So I'll just go with def here. Yep. I'll just go with the modular power here. Modular POW. So I'll just go with a base exponent here. Let me go with exponent. So this is fine. Let me consider mod as well. Yep. So within this function, let's initialize the result to 1. So this will accumulate base to the power of exponent modulo mod, right? So this one will be result equals 1. Yep. So the next part here would be we have to reduce the base modulo mod first to keep the numbers small, right? Accordingly with the what we had discussed in the approach actually. Yep. So let me go with base equals base modulo mod. Yep. So this is fine, I believe. So the next step would be we have to loop while there are still bits in the exponent. We have to loop while there are still bits in the exponent. So let me go with a while loop here. While exponent, while exponent greater than 0, then what we need to do here? So if the current least significant bit of exponent is 1, exactly 1, then we have to multiply the result by current base, nothing but the double mod we can call, right? So this we have discussed in the what do we call explanation part. So let me write the if condition here. See, I can just write it in this way. If exponent bitwise and 1, so let me consider one more this thing here, parenthesis here. So yep. So if the value is equivalent to the 1, then what we need to do here, result equals somewhere we discussed this one, yeah, at this one, result equals result into base modulo mod. Let me copy this one here. Let me paste it over here. Result equals result into base modulo mod, yeah, mod. That's what I said. Yep. So this is fine. Now what we need to do, so we have to square the base, meaning we have to move to the next bit, right? So we have done for the current bit. Next we have to move to the next bit, right? So we have to square the base, nothing but move to the next bit, keeping it modulo mod, right? So in simple terms, we will be going with this base equals base into base modulo mod as discussed in the explanation, right? So let me paste this one. Base equals base into base modulo mod. Yeah. Now let's do one thing. Let's do one thing. So now we have to shift the exponent, this one, right, by 1 bit, right? So this is nothing but the integer division by 2. See here, we have to shift the exponent right by 1 bit. I said we'll the same thing whatever we discussed in the explanation part, right? So we'll be articulating in the form of code every time I say the same thing, right? So that is the reason I ask you to listen to it carefully, right? So it might feel theoretical, this one sentences might feel boring, but you have to listen to it, because the same thing, the exact same thing, if we understand the this one approach part or the explanation part, the exact same thing will be articulating in the form of code. Yep. So this is fine. Now the final thing, the shift, let's shift the exponent right by 1 bit. I'll just go with exponent here, right shift 1. Yep. So let me give equals here. This is fine. The final part would be here. Let's do one thing. Let's return the result. Let's return the result. Yep. So this is fine, man. Now let's do one thing. Let's move on with the example one here, or let me do one thing. So we are done with the algorithm part. So this is easy, man. This is simple algorithm. This is easy. So let me take the example usage from the Google. Yeah. Just give me a second here. So I'll just paste this one over here. So the first example, we are just considering the small numbers for easy manual verification, right? So here we are just going with A1, E1 and M1 that we have assigned to the this one integers 3, 13 and 7 respectively. Now we are going with a print, this one statement just for the sake of interactiveness, right? Example one, compute what we are computing here, 3 to the power of 13 mod 7, right? A1, E1, M1, we are computing 3 to the power of 13 mod 7, right? So this is fine. Yeah. So here, what next print statement, we are just going with the modular power here. Modular power A1, E1, M1. We are passing the variables here. This is fine. Next, we are verifying with a Python built-in power. So here, this one, we have already discussed many languages, Python, POW, A, B mod, implement the same idea natively, right? So we are just going with a here, this one, built-in power. So this one power, we are passing A1, E1 and M1, right? So we have to get the output. So next we are just going with a large exponent. The same example, the same thing. We are just going with a large exponent here. Instead of 3, 13, 7. So this time it would be 2 to the power of 1000, 10 to the power of 9 plus 7. Mod 1 followed by 807, right? So this is fine, I believe. Yep. Yeah. 2 to the power of 1000. This one mod 10 to the power of 9 plus 7. This is fine. Yep. The same thing we are doing here. Similar to the first example. Yep. Now, what is the output that we need to get? We are done with the algorithm part, right? So what is the output that we need to get here? See, let's discuss the output part here first. See, just give me a second here. 1 second. Yeah. So we are going with this one, right? First example here. So we have to compute 10 to the 3 to the power of 13 mod 7, right? So 3 to the power of 13 mod 7. So that's what we are doing here in the first example. So modular power equals 3. Modular power equals 3, right? So just give me a second here. Yeah, modulo power 3. Result of our algorithm is 3 to the power of 13 mod 7. That is nothing but it is equivalent to the 3 itself. It is equivalent to the 3. You can just check manually, right? Powers of 3 modulo 7 cycle nothing but 3, 2, 6, 5, 3, 2, 6, 4, 5, 1, right? It goes on actually. And the 13th power falls to 3 itself actually. 13th power falls to 3 itself, right? So the output will be quite obviously 3 to the power of 13 mod 7 is 3. Yeah. So this one we are just printing compute 3 to the power of 13 mod 7, and then we are printing modulo power. So we are passing this one, right? So here the second in the second line, what we need to get here, modulo power 3 and built-in power also same. So we are just making use of the built-in function, and here we are going with the this one, the function modulo power, whatever we have used for this one function name actually, modulo power actually, right? So this is the built-in function, and this is the function we have written, right? So this algorithm that we have written, basically both has to give 3 itself, 3 and 3, modulo power and the built-in power, both we have to get 3. So this is the output that we need to get. First we have to get the same this thing here, compute 3 to the power of 13 mod 7, then answer 3 and 3 we have to get for the first example, right? So let's move on with the second example. Second example, what we are doing, we are computing 2 to the power of 1000 mod 10 to the power of 9 plus 7, this one. Yeah. So here, what are we doing? So the same thing we are printing here, compute 2 to the power of 1000 mod this one 10 to the power of 9 plus 7. Then we are just going with this one mod power and built-in power. For the mod power, you can just calculate in the same way that I said it for the this one. Example 1, right? So the output that we will get for this particular thing is, we are just taking the large exponent, right? So the output will be 688 688 42 3210 423210. So for this one built in also same thing, 688 so 423210, right? So this one when we calculate, right? So we have to get the this output when we for the second example. For the first example, it's the same sentence here. For the second and third print statement, we have to get output 3 and 3 respectively. For the second example, we have to get the same statement here. Example 2, compute 2 to the power of 1000 mod 10 to the power of 9 plus 7. Then we have to get this number, this value, 688423210. Same thing for the built-in mod, this one actually, power POW, what we have making use, what we are making use of here, right? So this is fine. So let me delete this one entirely. Now let me copy the file name. So I'll give Control J. Yep. Let me give Python followed by the file name dot py. Let me hit enter. See, compute 3 to the power of 13 mod 7. For the first example, we are getting this one correct. Yep. So modular power is 3 and the built-in power is 3. This one, both are same actually. This one we are calling this one, the algorithm that we have written, right? The function name that we are calling here, we have written this one manually, and this one can be used, this one, by with the help of this one, what do we call, built-in method in the Python, POW of this one, something. Yeah. So first comes the this one, what do we call, the integer, then the power, and then the modulo number, right? So this is fine. Yep, the second example, as I've said, 2 to the power of 1000 mod 7, the same thing that we are printing. We are printing this one first, then modular power and the built-in. So this one, the number that we discussed, 688 423210. Yep, so we are getting the desired output. So whatever algorithm that we have written works absolutely correct for this one. Absolutely correct here, right? So this is fine, man. Now we are done with the algorithmic part. We are done with the algorithmic part. As we are completely done with the algorithmic part, let's do one thing. Let me summarize whatever we have learned so far, man. Yep. So just try to remember these things. Modular exponentiation, also known as binary exponentiation, it computes what it computes actually, a to the power of b mod m, a to the power of b mod m, right? Efficiently by converting the exponent to the binary and repeatedly squaring the base while multiplying into the result when a bit is 1, right? It runs in, it runs in because of logarithmic b. This one we have discussed multiple times. So this one is very important. Because of logarithmic b time uses constant extra memory and avoids ever building the enormous value a to the power of b, right? So we can just use built-in functions like Python power. So this one, So I have already shown this one, power of a comma b, actually POW of a comma b. So this one a comma b mod, right? Yeah. So when available, they are implemented with the same efficient technique. They are implemented with the same efficient technique. So this is the algorithm behind the built-in function POW. So whatever we use in the Python basically. Yep. I hope this algo is completely clear. When doing CP, it's better to go with this one helper method, as this is fast. Actually, we can just make use of the modular power helper method for the calculation, right? So this will be helpful. Actually, this is fine, I believe. Yep. So let me delete this one. So this is it for the modular exponentiation algorithm. Next we will be discussing the discussing on the topic modular this one inverse algorithm. For now, this is it. Thanks for watching, guys.